Oftentimes you have sparse vegetation, and the fertility of the soil in these regions is fairly low. So a little bit of soil loss in some of these areas can have huge ecological consequences. So you can lose soil productivity or nutrient concentrations within the soil can be lost due to erosion. Erosion can also impact other ecological processes, such as the breakdown or decomposition of litter and the return of those nutrients back into the soil. It can also affect both the health and quantity of soil biota. And in extreme cases, erosion can lead to processes of degradation or desertification, as well as vegetation change. And so when we look on at landscapes here in the Southwest, oftentimes we can see that these landscapes are influenced by both wind and water-driven soil transport. Okay, and so it's the combined effect of these transport processes which gives rise to the total amount of erosion that you may find on a landscape. Both wind and water-driven transport are driven primarily by the climate as well as activities on the land surface. So land use practices such as prescribed fire and grazing can have a large influence on rates of wind and water-driven transport as well as climate variability. So when you combine these two factors, land use and climate variability, in some situations you can come up with extreme consequences, environmental consequences, which have huge ecological implications as well. So here you can see a picture of some vegetation. The top is still intact, but the root system is exposed. So this happened after a single wind event, a 12-hour wind event in the San Joaquin Valley in California in '77. And so this wind event was unusual in the fact that it was a very extreme wind event. So it happened in the winter, and it was a frontal system moving in off the coast of the Pacific. And we had winds in this storm that exceeded 70 miles per hour. So you had very strong winds. Now, the winds alone might not have been enough to produce that kind of effect in terms of soil loss, but when you combine that with land use activities, that's when you can start to see ecological consequences such as that. And so what we see in this picture at the bottom is basically a fence line, and on one side, on the right-hand side, much of the landscape looks like this, where you lost over a foot of topsoil overnight. On the other side of the fence, which was excluded from the grazing, the soil is still intact. So it's the combination of the wind and the land use which led to this. Obviously, the strong winds also passed over the area that wasn't grazed, but there was enough cover to maintain the soil. So when you combine these factors, it's important to consider the combination of these factors in land management. In addition to ecological consequences, dust has a lot of environmental health implications as well. This is a picture from a study site that I've worked on near Prescott Valley, and these are tailings from a copper mine. And there's two things that aren't very obvious in this photo. I mean, one thing that is obvious is it's very dusty, but what's hard to see is that it's actually not windy. It's not a windy day. The dust is there even on fairly calm days because these are tailings, and so the soil structure has been degraded and so forth. The other thing is that there are contaminants in the dust. It can't be seen, but these concentrations are extremely high, about 4,000 parts per million for arsenic and lead. And so this area was actually listed by the EPA as a Superfund site back in 2008. Just for reference, background concentrations there are around 40. Okay, so dust not only has important ecological implications, but also has important health implications. So going back to the ecological implications, we can imagine some of the effects of losing 60 centimeters of topsoil overnight in the area where the wind and land use activities were occurring. But there are also a lot of offsite effects related to dust transport, both ecological and hydrological. So for example, here off the coast of Africa, we see there's persistent plumes of dust. Now, this dust provides important nutrients for biogeochemical processes that occur in the ocean, places that are limited with nutrients such as phosphorus, as well as in a lot of tropical forest systems. The input of dust sustains the micronutrients in these systems. Dust can also impact the hydrology by affecting certain hydrological processes. So excessive concentrations of dust in the atmosphere can actually suppress precipitation, which then in turn can create more dust and further suppress the precipitation. And that happens by having an abundance of condensation nuclei within the atmosphere, and so you form a lot of small little water droplets that don't tend to coalesce and form rain droplets, so the moisture tends to move out of the region. So the dust has an effect when it's in the atmosphere. It also has an effect both ecologically and hydrologically when it lands in areas of deposition. So this picture up here shows a dust plume coming from the southwest going to the Rocky Mountains. And this is what it looks like when it gets there. The dust is deposited on the snow, and that can have substantial hydrological impacts. This is a picture of what one of these dust storms may look like from the Rocky Mountains. And again, this particular event came from the southwest, and the impact of this on the hydrological system can be pretty significant. So if we see clean snow, it tends to have a very high albedo. It reflects most of the incoming energy from the sun. But snow that's been covered with dust changes. And so now we actually have more of the solar energy being absorbed by the dust than reflected, giving us an albedo about 0.43. And how does that affect water resources? Well, it can have a large effect. This study is by Thomas Painter. And what they found, this is for total discharge in the Colorado River. And this black line here represents snow that's covered in dust. The blue lines represents snow that's not dusty. And what we see here is that the dust-covered snow melts up to 35 days faster. Yeah, this can have a huge impact on water resources, especially in the summer months when that water is needed both for vegetation and human uses as well. So when we look at this snow, it's not a simple story as just one event landing, because what you can see in the profile is an accumulation of different dust events. And as the snow starts to melt, the dust concentrates on top and becomes more and more concentrated through time, melting the snow even faster. In fact, studies have shown that dust on snow can have a greater impact in terms of the ability to melt that snow than a 4 degrees increase Celsius in temperature. So dust on snow is important in terms of water resources. In fact, it was estimated about 5% of the total runoff discharge in the Colorado River is lost due to snow, due to dust on snow. So how long has this process been going on? Is this kind of a recent process, or has this been going on for a long time? Jason Neff and some others were interested in that question, and what they did is they found some of these mountain lakes which basically have essentially no sediment input from streams. They're fed by snowmelt or groundwater recharge, and essentially the sediment that you find in there is from aeroline origin. And looking at two different lakes going down with depth, they were able to estimate the dust loading, the amount of dust deposition into those lakes. And we see similar patterns in both lakes. And so if we look at these points and try to put a timeline on that, we start to see a pattern to, prior to the European settlement, we had very little dust being deposited in these lakes. And around the period of 1850, that shot up a lot. And that actually corresponds pretty nicely with some of these laws that were passed, the Pacific Railroad Act, which kind of opened up the West to cattle grazing, and then subsequently the Taylor Grazing Act around 1930, you can actually see a decrease in the dust loading rate in some of these lakes. However, I should point out that even though the levels have come down, they're still up to about 500% greater than background levels prior to European settlement.
Jason, what state circles this?
Oh, good question. This is Colorado, the southwest part of Colorado. And, well, they're right there, San Juan Mountains. And so where's all that dust coming from? Well, the majority of it appears to be coming from Arizona. And this is during that time. So there's a joke up there. So we send them our dust, they send us their water. And so it's kind of a fair, well, not a fair trade-off, but we get the better end of the deal there. And so we can see in March, when snowpack is susceptible to melting, there's a lot of potential for dust deposition all the way into the late end of the season in May. And so in these areas, we also have other concerns more locally. One example would be I-10. And and Seth Munson compiled this just recently. And this shows a trend of the number of motor vehicle crashes in Arizona related to dust and the annual precipitation. And there is a pretty strong trend here. As we get less precipitation, we tend to have more vehicle wrecks. And so even if you just look at the top 3 years and combine the number of crashes, that's over 500 vehicle wrecks in just 3 years. So again, important human health implications. These pileups can be quite massive, can create a lot of havoc. For the most part, these areas where these dust plumes cross the highway, they're known to occur, but the solutions still remain elusive. And so currently not much is being done to address the problem. So that's something that people are starting to look into now, actually. So when we look in Arizona in the past 50 years or so, we can see that we've been relatively dry here. 20 to 40% less than our typical normal precipitation. And that is unlikely to go back to normal anytime soon if you believe some of the climate models. And this paper actually, it came out a while ago, but this is a summary of 19 different climate models, and they all predict kind of the same thing, hotter, drier regions here in the Southwest. And so the frequency and size of these dust storms is likely to increase with time rather than decrease, especially if you factor in land use activities. So that makes Arizona a pretty interesting place for me personally to study some of these effects of land use and climate change on soil loss and dust production. So at the Santa Rita Experimental Range, we have a few projects going on there where we've been monitoring dust and water erosion. And within some of these data sets, we have years that are exemplified really by climatic extremes. In this one particular year, we had a very wet August. I think it was actually over about 150 millimeters of rain. We had a 25-year rain event, followed essentially by the driest 9 months on the instrumental record, which dates back over 100 some odd years. So we had a very wet August and very dry period after, less than 20 millimeters of rain. At the same time, land use activities and management activities were undergoing. They had already been basically planned. We had this fire, which occurred right before the onset of the drought. The livestock grazing was ongoing in this area. And so one of the objectives was to try to determine how climate extremes and land use might affect wind, water erosion, and the total potential for soil loss. So this is cumulative precipitation on the Santa Rita Experimental Range for what we call a baseline year or a normal year. The average is about 350 millimeters of precipitation at the site. So about average precipitation with, the monsoon signature and some winter rains. When we compare that to precipitation from what we're considering a global change type year, we see here is the 25-year event followed by essentially no rain for 9 months. And what I did was try to compare the amount of water-driven transport during a normal year to that of what you might expect during one of these years with wet, dry extremes. And so here, this is the amount of water-driven transport that you might find during a normal year with normal precipitation. But during a year with especially a 9-month drought, essentially no water-driven transport occurred. And so we have a reduction in the water-driven transport. But when we look at the wind-driven transport, it's the opposite story. Here we see quite an increase over our baseline wind conditions. And this occurred by lots of small increments of small wind events, essentially. If you notice, there's just 1 or 2 large wind events in here. It's basically weekly, daily intervals of dust that accumulates, and progressively throughout the year, it adds up to quite a value. If we look at the ratio of wind to water-driven transport, in a normal year, these two processes are fairly comparable. For this particular year, wind-driven transport was about 3 or 4 times that of water-driven transport. But when we look at this year with wet, dry extremes, that ratio changed dramatically. Okay, so it went up by an order of magnitude. Now, the amount of wind-driven transport is about 40 times that of water-driven transport. And this is likely to have important ecological implications as well as potentially hydrological implications. So at the end of the year, basically, when you add up all of this, we came up with a value around 2,000 grams per meter of dust or sediment being moved by wind. Okay, so that is this line right here at the bottom. I wanted to also see how land management practices might influence that value. And so here we have both prescribed fire and grazing kind of superimposed upon the drought conditions. And what we see, the effects of both fire and grazing increase the amount of wind-driven sediment transport essentially by an order of magnitude. So land management practices can have an effect on soil loss, and that effect can be exacerbated under climatic extremes. So perhaps if we didn't have 9 months of essentially no rain, that value would be an order of magnitude greater. But it's the interaction between climate change and land use that is of interest here. So with all this material blowing around, we wanted to find out if it's leaving the site or is some of it being deposited underneath shrubs or in grasses. And so most landscapes can be thought of as a mosaic of 3 different patch types. You have grasses, bare patches, and shrub-dominated patches. And so we put some samplers in front of these patches and behind them to try to estimate how much dust and other resources like organic material and nutrients was being captured by these patches. It's kind of a closer look at it. There's a bare patch, grass patch, and shrub patch. What we found were that the bare patches were actually producing sediment, whereas the grass patches and shrub patches were collecting sediment. In a disturbed environment, the main difference is that the grass patches went from a sink where they captured sediment to a source where they actually were producing sediment. And to look at that in more of a graphical display, we see, again, in the undisturbed conditions, only the bare patches were producing sediment. But most of the sediment and other resources, will be captured by either shrubs or grasses, depending on the density of the landscape. But when disturbance is factored in and you lose your herbaceous cover due to prescribed fire or grazing, then you end up with 2 sources that are producing sediment, and oftentimes only the woody material left will actually create enough shelter to deposit some of that sediment. And that's one of the reasons you can get these islands of fertility developing. So I wanted to put these results in kind of a broader context at the landscape scale. And so what we decided to do was to plot these results along the gradient of woody plant canopy cover. So at the Santa Rita experimental range, there's about 5% woody plant canopy cover, and we plotted a dust value of roughly about 4.5 grams per meter per day there on average. I then looked in the literature for other undisturbed areas and how dusty those areas were, and plotted that to try to look for some trend or pattern in terms of alien transport across these different types of ecosystems. And there's not very many data points because there aren't very many studies that monitor wind erosion for multiple years in areas that are essentially undisturbed. A lot of people like to go to areas that are burned or grazed. So I also plotted the points from disturbance along this graph too. It doesn't look like a large increase, but this is on the log scale. So if we look at the effects of fire and grazing, we see clearly the amount of sediment increasing. Then looked in the literature for other points of disturbance, again, trying to find some pattern to the amount of potential sediment transport by wind, as a function of woody plant canopy cover. And we can see that there's kind of a lower limit of transport that corresponds with undisturbed systems, and that tends to peak around shrublands. And then for disturbed systems, we see that grasslands essentially have a greater potential to produce more wind erosion, because if you have disturbance that takes out all the grass, there's essentially no woody component left to capture any sediment. And this is again for wind-driven sediment transport. So these are the results from Santa Rita experimental range. Just want to take the last couple minutes to plot some preliminary results from Los Cienegos. We have 2 sites. There's an abandoned ag field and a native grassland. This is what the native grassland looks like. I'll go into a close-up image of this. That's the abandoned ag field. And so in this area, you can see there's kind of a gradient of vegetation where at the lower end you have, it's dominated by annuals. And then as you move up to the upper end, you start to have perennials and shrubs. So we put 3 transects out there where we're monitoring wind erosion along those locations. The native Saskatoon grassland, we're interested in these bare areas up here and some of the potential causes for those areas. And so we have a transect up there, and this is what it looks like. I mean, these areas are quite bare. There's essentially no grass growing. Right on the other side of the road, it's quite a different story. The grasses are healthy, bare spots are quite minimal. And there's another area over here that's even more vegetated that has essentially no patches there. So when we plot these in this framework, we see the abandoned ag fields. That compares closely to a native grassland following a fire. And so you can see the amount of sediment transport is kind of high. When we move to the upper end of the field, the amount of sediment transport decreased quite a bit. Here's the native Saskatoon grassland with good cover, lowest value that I've measured so far. Again, these will change. These are based on just a couple months of measurements. As we get more data, these values may move around slightly. But this one was pretty interesting to me. This is the dustiest site that I've personally measured, and it's literally right across the road from the native grassland. So if we look, these two sites are right across the road from one another, and these are right upslope and downslope. And so, real quickly, I just wanted to take a look at this bare area and maybe toss out an idea of one potential problem that could be occurring here. We took soil samples along the transect, measured salinity and sodicity, and we found some interesting patterns. It's kind of hard to see, but if we look at just the areas where there's high vegetation cover, we see that the EC is less than 1 in all those locations. And then areas just 10 meters away, the EC value is quite high. We need to go back and collect more soil samples. Again, these are preliminary results, trying to see if salinity or sodicity might be a problem in some of these areas, because essentially there's no drainage here. And so this road may be part of the problem, but I suspect when it rains, this water ponds and has nowhere to drain to, and so you have a buildup of these salts. You see the same thing with sodium. We have the sodium absorption ratio. I just plotted sodium concentration just to give you an indication that values are essentially 50 times that of the surrounding area. These are just 10 meters away. So in conclusion, basically soil erosion is driven by wind and water-driven transport. It's affected by both land use activities and climate variability. And the last thing I wanted to mention is that with projected climate being hotter and drier, this portion, the wind-driven transport, is likely to become more ecologically important and hydrologically important with time. So I'd like to acknowledge my collaborators and sources of funding.